If you're a PUC student who's confused about limits in calculus, this video shall help you get a get clearer on the idea of limits and also show you the purpose of limits in calculus. I'd like to begin this with a little story. This is a story of a boy named Ali, a genius child. Ali has done very well in his exams and was off with his family for a vacation to Mysore for a well-deserved holiday. However, after 2 hours of traveling on the Bangalore-Mysore road, their car is flagged down by a policeman. The policeman tells Ali's father, "Sir, you're going above the speed limit, sir. Please pay the fine." Or, we can also adjust, sir. Ali's father was worried. But Ali says, "Hold on, sir. My father was within the speed limit and I can prove it." And then Ali displays his mathematical superpowers. He takes out his notebook and explains, "You see, sir, the equation of distance over time traveled is distance equals to initial velocity into time plus half into acceleration into time square. Or s is equal to ut plus half at square. Since initial velocity is 0, we can simplify the equation to s is equal to half at square. And sir, you probably already know that. You must have learned that in 6th grade physics. Anyway, say we draw since our acceleration was 30 kilometers per hour square, say we draw a graph of the distance traveled being the y-axis, time being the x-axis. We use the equation y is equal to half ax square, a being 30 kilometers per hour square. This is what our graph will look like. You, sir, stopped us 2 hours after you traveled, which was this point here. And I can prove to you that the speed at this point was within the speed limit. Now here Ali has a problem. To prove the speed at this point and this point only, Ali needs to calculate the slope at this point. He tries to do that by drawing a tangent at that point. What's a tangent? A tangent is a line that just skims the line at a point on the curve. It touches one point and no other point. Now, though Ali has a tangent, he doesn't have any other point on that tangent to work out the slope. And one cannot work out the slope with just one point. Say I draw an axis here and give a point here, x comma y, and ask you, "Hey, please give me the slope at this point." You would say, "Arif, you would be nuts. How am I to give you slope at that point?" Even if I were to draw a line or a tangent at that point, what would the tangent look like? Would it be like this, or like this, or like this? To have a slope, I need 2 points, and that's when I can work out the formula of a slope, mainly being delta y over delta x, or y minus y1 divided by x minus x1. Now here Ali has just 1 point. Ali then uses the help of a secant. What's a secant? A secant cuts the line at 2 points. This, for example, is a secant and cuts the curve at these 2 points. Well, now at least he can work out the slope of the secant. So first we need to work out the coordinates at P. You can see the math is pretty simple. Just have to put in x. We know that x is 2 and you get the coordinates at P. To work out the coordinates at Q, you put x as 1, you get the coordinates at Q. And once you put these values into this, the slope equation, you get the slope to be 45, of which delta x is 1. Now let's plot a table of delta x and the slope of PQ. So when our first value, when delta x is 1, slope of PQ is 45. Now what we wanted was the slope of the tangent, the green line. What we have is slope of the secant, which is not good enough. So let's move our secant a little bit closer to the tangent. Let's say we bring Q halfway to where x is 1.5. Now let's work out the coordinates at Q. We see we have the coordinates at Q, and now let's work out the slope of PQ. We see the slope of PQ is 52.5 and delta x is 0.5. We're getting closer to the tangent, but not there yet. Let's move Q even close. Let's move Q to 1.9. And then what is the slope that we get? And when we do the math, we see that the slope of PQ now is 58.5 when delta x is 0.1. Still, it's closer to the tangent, but still not there yet. Let's move x even closer. Let's say x is now 1.999. It's perhaps practically over the tangent, but still not there yet. Yet let's work out the slope. And when we do the math, we see that the slope of PQ now is 59.99 and delta x is 0.01. Okay, let's recap what we have done till this point. What we wanted to do is find the slope of the tangent at point P. We first tried to find the slope of the secant PQ. Then we drew a sequence or a series of secants. We have drawn a series of slopes. The slopes never reaching the tangent, but they're constantly coming closer and closer. And graphically we can see that the tangent at P is the limit of that sequence of slopes PQ. The tangent is the graphical limit. But what is the mathematical limit? We see the mathematical limit is coming closer and closer and closer to a number, from 45 to 52 to 58 to 59.99. What could be the mathematical limit? Could be 60. Let's take one more value and find out. So let's say x is 1.99999. That gives us delta x is 0.000001 and the slope of PQ to be 59.9999. It is approaching 60 without ever reaching 60. So let's express this mathematically now. So the limit of the value of the expression delta y over delta x, which is also the slope of the tangent at P, of delta y over delta x, as delta x approaches 0 is 60. We see as delta x decreases and decreases without ever reaching 0, it can't. There is a boundary that the slope will not cross. That is the limit. Graphically it's a tangent, mathematically it's 60. And hey, guess what? We just worked out the speed at time 2 hours is 60 kilometers per hour, which is way below the speed limit. And you know what? We just did really high funda differential calculus to get to that speed. Not too bad, huh? You kind of get a feel how this can be useful. It's actually incredibly useful. Say you're a scientist at ISRO and you want to work out the speed of when you launched a rocket at 4.5 seconds after launch. You would have to work out the slope of the tangent 4.5 seconds after launch. Or you're an economist with the RBI and you want to work out the rate of inflation at a point in time. You would again use differential calculus and the idea of limits to work out the rate of change at that point in time. So if you were to express this mathematically, we would say that the rate of change at a point in time, at a point in a graph, say xy, would be expressed with the equation dy by dx as long as the limit of delta x is approaching 0 is delta y over delta x. And this is the differential at xy. Anyway, by this time the cop realizes he's not going to get anything out of the situation. Ali and his father make most of his confusion and scoot off to Mysore. Hope you have a clearer understanding of limits. It can be used to not just confusing cops but for others as well. Take care, drive safely. Bye.